Welcome to QML Arena by Quantum Innovation. This is a learning platform designed to develop and improve your skills in quantum machine learning, driving you through the analysis pipeline, step by step. Let us get started with our classification demo. In the first place, we need to choose a data set for our classification task. In the Data and Task tab, we can select different source data. The user may upload their own files or draw a dataset. Alternatively, the user can exploit one of the toy dataset already available. For example, we can use one of the sklearn classification datasets such as the Moon dataset, the Circle dataset, or the Iris dataset. In the bottom right panel, we can explore a visualization of the data. This representation is dynamic and it changes depending on the dimensionality of the data. For example, the Iris dataset is 3D, so each feature is plotted against all the others. When many more features are available, such as in the breast cancer dataset, we can choose which features to actually use. We can do so in the Data Selection menus. We can pick an individual feature, as in the default case, multiple features, or all the features. We can also decide which column we want to use as a target or, equivalently, as a class. For the toy datasets, the default choice is predefined, while for user-uploaded datasets it gets deduced. In any case, it can be changed afterwards. Notice that when more than 4 features are used, we use principal component analysis to reduce the dimensionality and plot the projections on the first 4 components. The left panel shows the data frame containing the actual values. When a dataset contains categorical features, those are automatically one-hot encoded for future usage in the models. For this example, the class, benign or malignant, is encoded into 1s and 0s respectively. Let's now go back to the Moon's dataset, composed of 2 features and 2 classes. We will add a bit of noise just to make the task a bit more challenging. If you desire more details about a preloaded dataset, you can check the description drop-down. Simply put, our task will be to train a model that learns to separate the blue from the red data points. Having decided on our data, we can proceed to the Preprocessing tab. Preprocessing regards every analysis step we take before the actual model fitting. Keep in mind that preprocessing parameters must not be learnt on the whole dataset, but only on the train subset. In the platform, we will decide the train test split in the Pipeline tab, so here we will only have a preview. We can proceed by selecting a preprocessing step. We can normalize using the standard scaler, the min-max scaler or the quantile transformer, or perform principal components dimensionality reduction. For example, let's go with the quantile transformer. This transformer uses the empirical cumulative distribution function to transform the features into a target distribution. For example, the uniform distribution. Once set, the configuration hyperparameters are displayed in a box next to which we can explore a preview of the effect of the transformation on each feature. Here we can see the effect on the first feature, x1, and play with the slider to see the distribution before and after the transformation. The bottom axis shows the feature values before the transformation, while the top axis shows the transformed values. As expected, the quantile transformer adjusts the feature distribution to approximate a uniform distribution. Notice that we can actually chain multiple preprocessing steps in a row. For example, we may add a standard scaler, which will leave a uniform distribution unchanged, but modify its dynamic range. We can now proceed to the Estimator tab, the core of the analysis. The estimator is the algorithm that acts on the preprocessed features in order to achieve the required task. In this case, predict the class, red or blue. The default choice for a classification task is a quantum support vector classifier. As shown in that description, QSVM maps data to a quantum Hilbert space via quantum feature maps, effectively performing a kernel trick in the quantum domain. This creates a kernel matrix, that is then evaluated by a classical SVM to perform the classification. In the estimator configuration, we can select the circuit hyperparameters. For example, we can change the number of qubits, or we can change the type of encoding and its hyperparameters. Let's go with the default case. The circuit is performing the following operations. The Hadamard gates, H, create superposition, allowing qubits to represent multiple states. The rotation gates, R, encode classical features as rotations on qubit axis. The symmetric I-swap gate entangles qubits to represent feature interactions jointly. The repeated rotations re-encode features, increasing the circuit's expressiveness. Let's now proceed with the pipeline tab. Behind the curtains, the pipeline chains all the preprocessing steps and the estimator into the actual model. Here, we can choose the assessment protocol. The basic choice is the simple train, validation, test split. The train set is used to learn the model parameters. The validation set is used to check the model hyperparameters. Test set is used to assess the model performance. With the sliders, we can select which fraction of the data goes in each subset. We can now proceed with the Run Fit tab. In this tab, we launch the fitting process. In this platform, we are using quantum simulators, so the actual calculations happen on a classical device. Let's run the fit, and once the model training is completed, we will proceed to the Results tab. This tab presents several performance diagnostics as evaluated on the test set. In the top row, we can see several default metrics, such as accuracy, precision, recall, and F1. For this run, we obtained a global accuracy above 90%. In the bottom row, we can see the ROC curve, the confusion matrix, and the probability surface. Probability surface represents the model's estimated probability all over the feature space. This is estimated by simply evaluating the model on a regular grid of points or spaxels. The spaxels are color-coded by the most probable class, and their intensity is proportional to the estimated probability. In this visualization, the full circles are the test data correctly classified as blue or red. The samples drawn as an X represent instead the misclassifications. Let's now go back to the estimator and try a different algorithm. This time, we are going to try a hybrid neural network. A hybrid neural network is a network that interlaces classical neuron layers with quantum layers. Let's build the one for our case, the Moon dataset classification task. In the estimator schema, you can see that the platform initialized the network with just 2 layers. The input layer is composed by the dataset features, therefore it has dimensionality of 2. The output layer matches the encoded classes, 0 or 1, and hence it also has dimensionality of 2. We can make the network more complex by adding layers, using the menu on the left. We will first add a dense layer composed of 32 neurons and rectified linear unit activation function. So far, this network is fully classical. However, we can follow up the dense layer with a quantum layer. In the hyperparameter selection, we can choose how many qubits we wish to use. We can set this to 4. The device type is left to the default, since we are using simulated quantum calculations. Here, we can also select the data embedding, that is, the process of encoding classical input data into quantum states. We will use ankle embedding, which encodes by applying rotations to qubits based on input values. That means that the data incoming from the previous layer will be used to rotate qubits. This step is followed by an entanglement. Entanglement is a quantum connection between qubits, linking their states, and can be of 2 types. Basic entanglement is a local connection between neighboring qubits. In strong entanglement, each qubit may be entangled with multiple or all other qubits. Once added, the quantum layer appears in the estimator schema. Notice that we cannot connect directly the 32 neurons layer with the 4 qubits layer. For this reason, a connecting layer is automatically added in between. The role of this layer is solely to reduce the dimensionality to the one required by the quantum layer, from 32 to 4. The parameters of the whole network will be learned during the training. For the classical part, those are the weights and biases of each layer after the input. For the quantum layer, those are the gate rotation angles. That is, as the network trains, it also learns which are the optimal rotations to be applied when embedding data into the quantum layer. Notice that in hybrid models, the optimization still happens classically. That is, no quantum calculation is involved. In fact, the loss is calculated by comparing the predictions to the ground truth in the classical framework. Since this is a classification task, the loss is set to be cross-entropy. An optimizer such as Adam can be used to estimate the gradient step at each iteration. In the Configure Estimator menu, the user can experiment with several hyperparameters, such as learning rate of the optimizer, the number of epochs, and batch size. We will leave these quantities to their default values and see what happens when we train this network for 20 epochs. We therefore proceed to the Run Fit tab and launch the fit. As you can see, for the neural networks, the platform dynamically displays the training evolution. On the left panels, you can inspect the loss and accuracy history of the train and validation sets. The right panels show the output of each individual layer as it evolves along the training steps. Recall, our network had a dense layer, followed by an activation function, then a connecting layer, a quantum layer, and finally the output. Therefore, we have 5 panels. To be specific, these panels present the projections of the layer's output on the first 2 principal components. This trick helps us build intuition about how data is transformed by each layer, no matter its dimensionality. This is especially practical for layers with high-dimensional outputs, such as the dense layer with its 32 dimensions. Notice how the network strives to achieve a simple representation in the output layer, so that the classes become linearly separable. This effectively summarizes the essence of neural networks, that is, find a feature transformation that simplifies the task. After the fit is completed, we can go back to the Results tab and check if we improved on our results. If not, we can keep playing with the arena. Notice that, throughout the platform, you can interact with QML Gladiator, our chatbot. QML Gladiator is context-aware, so you can query it with what you need to understand in the current page. For example, we can ask, "What are we seeing here?" After a few seconds, you will get more info about the current tab. Finally, one of the notable features of QML Arena is that you can export a Python notebook. Just click on Generate Notebook, wait an instant for it to be compiled, then download it. Once loaded, we can see that the notebook provides the code to reproduce the steps that we set up in the platform. We can execute the code cell by cell and get to the results we previously obtained. Notice that the optimization is stochastic, so the actual values may slightly vary. You can now use this notebook as a convenient starting point for a more in-depth analysis. Just customize it to your needs. You can access a demo of our platform at qml-arena-demo.streamwith.app. If the app is idle, do not worry, you will just have to wait a minute or 2 for it to resume. Experiment, learn, and most importantly, let the best model win.